Problem 47 says, on the same side of a straight river, here's the river right here, are two towns, town 1 and town 2. And the townspeople want to build a pumping station S to get water to the towns from the river. It's at the river's edge, and pipes extending straight to the two towns are shown right here and right here. Question is, where should the pumping station be located to minimize the total length of the pipe? X is the unknown we want to solve for. What should X be to make the total length of the pipe as small as possible? X could be really small. Maybe you want to put the pumping station really close to town 1. Then it's really close to town 1, but it's pretty far from town 2. It could be right here, closer to town 2, but then it's further from town 1. Where should we put it to make the total distance a minimum? Let's redraw it so I don't have to write in my book here. Got a couple right triangles. I hope it's pretty clear that you want to use the Pythagorean theorem. Call this D1 for distance 1 and this D2 for distance 2. We want to minimize D1 plus D2. That would be our objective. D1 plus D2. We got to get that in terms of X. What is that total distance in terms of X? You have to use the Pythagorean theorem. D1 is the hypotenuse of this right triangle of legs length 1 and X. So D1 is the square root of 1 squared plus X squared. You can't get rid of these square roots because you're adding 2 square roots. From the other triangle, D2 is the square root of this side squared is 4 squared. What's this side? Little problem solving. It's got to be 4 minus X. If that length is X, and the total length here to here is 4, the length here to here has got to be 4 minus X. And if you got this far, that's pretty good. That's a good chunk of what you should have done. But there's still more to do. We still need to minimize this function. We've got to take its derivative, set it equal to 0, and solve for X. It doesn't seem like it's necessarily going to be so easy. But let's see what happens. Square root is the same as 1/2 power. So this is the same as X squared plus 1 to the 1/2 power. Or 1 plus X squared if you prefer. 1/2, 1 plus X squared to the negative 1/2. Don't forget times 2X from the chain rule. Here, you could simplify what's under the square root. And if you did that, that's fine. I think it turns out to be easier to not simplify it, actually. I mean, I'll make the 4 squared a 16. This thing is being raised to the 1/2 power. Again, bring the 1/2 down. Turns out to be best not to bother expanding this part right here. But I'm not quite done with my derivative. I need to also use the chain rule here. Derivative of this is 0 plus, okay, again, I'm not going to expand this. I'll just bring down the 2 and have a 4 minus X to the first power. Then the chain rule again will give me an extra factor of -1 because the derivative of 4 minus X is -1. It's very tricky, easy to make a mistake there. I'm setting this equal to 0, and then I'm going to solve for X. Set all this equal to 0 and solve for X. Ha, ha, ha. How in the world? Okay, it does simplify. Those 2's cancel. These 2's cancel. The things with -1/2 powers can go in the bottom as a square root, right? Because -1/2 power means 1 over that thing to the positive 1/2 power. And that negative sign there means I think I want to add this thing to both sides without the negative sign. And so I'm going to get the equality of X over square root of 1 plus X squared coming from this term right here with looks like 4 minus X over the square root of this thing. That looks like probably if I've not made a mistake, is the equation I want to solve. It's a little nicer looking. We probably want to get rid of the square roots, maybe square both sides. And then we got two fractions being equal, we can cross multiply. Maybe that's a good idea. Let's square both sides first. That'll get rid of the square roots. And again, I could expand 4 minus x squared, but maybe it's better not to. Now cross multiply. We'll get a fourth degree equation. Doesn't sound so pleasant. Is it still solvable? That's hard to say. Distribute this through, we get 16x squared plus x squared times 4 minus x quantity squared. I think we will get some cancellation. Distribute this through the parentheses. Yeah, okay, I can see some cancellation going to happen. What's going to cancel? These two things are going to cancel because they're the same thing on both sides. If I subtract that from both sides, they both go away. And it simplifies down to a quadratic. How about that? Okay, maybe now I'll expand this. Get 16 minus 8x plus x squared. I'm getting close. Maybe get everything on the left. Subtract x squared from both sides. Add 8x. Subtract 16. We get a quadratic. Now I guess use the quadratic formula. By the way, I have no idea whether this is still right or not. It's possible I've made a mistake. Let's just see what happens here. Doesn't look so easy to factor, so I'm going to use the quadratic formula. Negative 8 plus or minus square root of 8 squared 64 minus 4 times 15 times negative 16 over 2 times 15. That's the quadratic formula. Negative 8 plus or minus square root of 4 times, well, can I do this in my head? I better not. 4 times 15 times 16 gets added to 64 because 2 minuses make a plus. I have 1,024 in there. I do happen to know that is a perfect square. It's 2 to the 10th power. So it's 2 to the 5th squared. It's 32 squared. Its square root is 32. Negative 8. This is making me confident that it's right now. Plus or minus 32 over 30. If we use the plus thing here, it'd be negative 8 plus 32 is 24 over 30. If you use negative 8 minus 32, you get negative 40 over 30. These fractions simplify to what? 4/5 and negative 4/3. But x is a distance, so we better use the 4/5. That must be the answer. That's such a nice number. It must be right. X equals 4/5 or 0.8 miles. Looks like it's probably the optimal value of x to choose to make the d1 plus d2 a minimum. Is it really a minimum? You'd want to graph the original function to see. I mean, yes, we could use the first or second derivative test to verify it's a local min, but we want it to be a global min anyway, so we might as well just graph the function. So I'm going to plot the original function. F of x is square root of 1 plus x squared plus square root of 16 plus 4 minus x quantity squared is the function I want to enter and plot. As far as the domain values for x here, x can really only go between 0 and 4, right? For the application to make sense, at least. So plot this between 0 and 4. There's the graph. It does look like it is perhaps minimized when x is 0.8. Yeah, and it's definitely a minimum. And Mathematica solve for where f prime of x is 0. Let's see. Yep, 4/5, much quicker.